Hello, and a very warm welcome to this course module. It is great to have you here. We are about to embark on a critical stage of your development as a cybersecurity professional. My name is Dr. James Morgan. I will be your guide through this chapter. We are about to dive deep into the foundational elements every security analyst needs to master. Think of this as the essential toolkit you will carry every day. Without these fundamentals, analyzing threats or defending networks is like building a house on sand. It won't hold when the pressure is on and the digital winds start blowing. So, let's get ready to build a solid foundation together. This module is designed for students like you who want to move beyond headlines and understand the mechanics of cybersecurity. We take a pragmatic approach. Not abstract theory you forget when the lecture ends. Instead, practical, real-world knowledge for use in a Security Operations Center SOC. We keep language clear and concepts grounded. We will demystify IT infrastructure and software, make it accessible and even a little fun. We will be human about it. Cybersecurity is people protecting people from malicious actors. Actively engage with the material. We will have prompts to encourage reflection. When we discuss a concept, pause and think how it applies to environments you know. Your university's network, a part-time job, your home setup. Connect ideas to tangible examples to deepen understanding. We will have prompts to encourage reflection. This active learning will turn you from spectator to participant, the mindset a proactive analyst needs. Our journey is structured and clear. We move step by step, so each concept builds on the last. Don't feel overwhelmed. We start from the ground up. Every topic is chosen because it's essential for your future role, from the servers that run our world to the code that makes them tick. We will explore the landscape you will defend. Consider me your co-pilot. I will navigate complexities and ensure we land safely with a cargo of valuable knowledge. Fasten your seatbelts, get your notebooks ready. Let's begin this exploration. We are now officially diving into Chapter 1, which is titled Technology Underpinnings. This chapter forms the bedrock of cybersecurity foundations. Why do we start here? Because you cannot defend what you do not understand. A cybersecurity analyst who does not grasp core systems is at a disadvantage. How a network is built, how an operating system functions, how data is stored. They might follow a playbook, but lack the intuition and deep knowledge to hunt for novel threats or respond to a sophisticated incident. This chapter gives you that core understanding so you can operate from strength and confidence. This chapter is your map to the digital world's core components. We will explore the fundamental pillars of modern technology, every application, every transaction, every piece of data. Compute physical machines, compute virtual machines, storage systems that store information, networking networks that connect everything. It's the invisible scaffolding of our digital society. As a future analyst, know this terrain intimately, its strengths, its weaknesses, the nooks and crannies where attackers hide. This chapter provides essential context, the lay of the land before battle tactics. These concepts aren't just academic. They are the daily language of a SOC. Terms like virtualization, containers, high availability, DNS are critical systems you will monitor. Understand Type 1 hypervisors. Understand Network Attached Storage, or NAS. Understand Storage Area Network, or SAN. This knowledge is crucial to determine scope or impact of incidents. Ask smarter questions. Interpret alerts more accurately. Communicate with IT and engineering. This chapter is the prerequisite for what follows. Analyzing logs. Hunting for indicators of compromise. Performing incident response. When a senior analyst asks you to check logs on a domain controller or investigate traffic from a container, you must know what those things are and where to look. This chapter fills gaps and builds a solid baseline. It is the groundwork to build a skyscraper of cybersecurity expertise. You might be wondering, I want to be a security analyst, not a network engineer or a system administrator. Why do I need to know all this in such detail? That is a fair question, and the answer is simple: context is everything. As a cybersecurity analyst, your primary job is to detect, analyze, and respond to threats. These threats do not happen in a vacuum. They occur on servers, they travel across networks, and they exploit vulnerabilities in operating systems and applications. Without a solid understanding of this underlying technology, you are essentially trying to solve a puzzle with half the pieces missing. You might see an alert, but you will not understand its true significance or its potential impact. Let's consider a practical example. Imagine you see a suspicious process running on a server. An analyst with no infrastructure knowledge might just see a strange name and flag it. But an analyst who understands operating systems will ask deeper questions. Is this process running with elevated privileges? What files is it accessing? Is it making network connections? Which user account launched it? An analyst who understands networking will then ask, where are those network connections going? Is it communicating with a known command and control server? Is the traffic encrypted? This deeper level of inquiry, which is only possible with foundational knowledge, is what separates a junior ticket closer from a skilled threat hunter. Furthermore, your workflow as an analyst is inextricably linked to these core systems. When you are triaging an alert, you will be pulling logs from various sources: Windows event logs, Linux syslog, firewall logs, DNS query logs. To make sense of this data, you must understand what normal looks like. You need to know what a standard DHCP request looks like, or what typical Active Directory authentication traffic entails. This baseline knowledge is what allows you to spot the anomalies, the single malicious DNS query hidden among millions of legitimate ones. Without it, you are drowning in data, unable to distinguish the signal from the noise. Ultimately, mastering these fundamentals of infrastructure, networks, operating systems, and even basic coding empowers you to be a more effective and self-sufficient analyst. You will be able to automate repetitive tasks with simple scripts, build your own tools for analysis, and speak the same language as the engineers who build and maintain the systems you protect. This not only makes you a more valuable team member, but also makes your job more interesting and rewarding. It elevates your role from simply following procedures to actively engaging in problem solving and investigation. This chapter is your first and most important step toward becoming that kind of proactive, knowledgeable, and confident analyst. So what exactly can you expect to learn in this chapter? We have structured our journey to be comprehensive yet digestible. We will begin with the big picture infrastructures and architectures. Here, we will unpack core concepts like compute, storage, networking. We will contrast deployment models, on-premises data centers, cloud-based models, hybrid models. We will demystify virtualization and containers. You will learn what a hypervisor is, how containers are managed, why these concepts matter for security. Next, the networks, the pathways that connect everything, how an enterprise network is architected, the edge, internet, facing, the core, critical data, essential security controls to segment networks, firewalls, access control lists, ACLs, proxies, secure remote access, VPNs, SD, WAN adoption, network monitoring visibility into traffic flows. From there, Operational Technology, OT. Industrial Control Systems Overview. Factories, power plants, critical infrastructure. How OT differs from IT. Safety, availability. Common OT components, PLCs, SCADAs, the Purdue model for OT segmentation. Finally, software, the heart of every device. Operating system fundamentals, Windows, Linux. How OSs manage processes, memory, file permissions, coding basics for analysts. Not a developer course, practical scripting skills. Python, PowerShell. Use code to automate analysis, parse logs, interact with security tools. This entire chapter is the launchpad for everything that comes next. All right, let's lay the first stones of our foundation, the three fundamental pillars of any IT infrastructure: compute, storage, networking. These are the essential building blocks that power every digital service, a simple website to a global banking system. When we talk about compute, we mean the processing power that runs our applications. This is provided by the Central Processing Unit, or CPU, and the Random Access Memory, or RAM, inside servers. Think of the CPU as the brain doing the thinking, and RAM as the short-term memory it uses to work on current tasks. As an analyst, you will often investigate unusual CPU spikes or memory usage, as these can be indicators of malware or other malicious activity running on a system. Next up is storage, which is simply where our data lives when it is not being actively used by the CPU. This is the long-term memory of our digital world. Storage comes in several different flavors, and it is important to know the difference. Direct Attached Storage, or DAS, is the simplest form, where hard drives are physically connected to a single server. Storage Area Network, or SAN, is a high-speed, dedicated network of storage devices that appears to servers as if it were locally attached, often used for critical databases. A network-attached storage, or NAS, is a file-level storage device connected to the main network, great for sharing files among many users. Finally, object storage is a newer method used heavily in the cloud, where data is managed as objects, perfect for storing vast amounts of unstructured data like videos or backups. The third and final pillar is networking. This is the glue that connects everything together. It allows the compute resources to talk to the storage systems and enables users to access the applications. Networking is built upon devices like switches, which connect devices on a local network, and routers, which connect different networks together, including connecting your organization to the internet. As a security analyst, the network is one of your most critical domains of observation. You will be analyzing network traffic to hunt for intruders, identify command and control communications, and detect data being exfiltrated from your environment. Understanding how data moves from point A to point B is absolutely essential for effective defense. These three pillars, compute, storage, and networking, are not independent silos. They are deeply interconnected. An application running on a server, which is compute, might need to pull customer data from a database living on a SAN, that's storage, and then send the results over the corporate LAN and the internet, which is networking, to a user's web browser. A disruption or compromise in any one of these pillars can have a cascading effect on the others. Your job as an analyst is to understand this symbiotic relationship. You need to be able to trace an event across all three pillars to get the full picture of what is happening, because that is exactly what attackers do when they are trying to find a way into your systems. Now that we understand the core components of infrastructure, let's talk about where it physically or virtually resides. The traditional model is on-premises, or on-prem for short. This means an organization buys all its own hardware servers, Storage arrays, networking gear. They house it in their own data center or server room. The company is responsible for everything: physical security, power and cooling, hardware maintenance, and software management. Security-wise, on-prem gives complete control, but also full responsibility from door locks to operating systems. Contrast that with the cloud. Cloud computing means renting compute, storage, networking resources. Examples: Amazon Web Services, AWS, Microsoft Azure, Google Cloud Platform, GCP. Remember the shared responsibility model. Provider secures the cloud itself. You secure what's inside virtual machines, data, applications. Cloud misconfigurations are a top cause of breaches, which leads us to hybrid. Hybrid equals a mix of on-prem and public cloud. Orgs keep sensitive data or legacy applications in on-prem for control or compliance reasons, and use cloud for new development, scalable web apps, disaster recovery. Hybrid gives flexibility, but increases complexity. Analysts need visibility and consistent policies across both footprints: on-prem, physical appliance logs; cloud-native, API call logs, and cloud security alerts. Hybrid. You must do both and track threat pivoting between environments. Understanding these models is your first step to defending the landscape, no matter where it is located. One of the most transformative technologies in modern IT is virtualization. At its core, virtualization allows you to run multiple, isolated operating systems on a single physical server. This is achieved through a special piece of software called a hypervisor. The hypervisor is a layer that sits between the physical hardware and the virtual machines, or VMs. It is responsible for carving up the physical resources and allocating them to each VM. It allocates the CPU. It allocates the RAM. It allocates the storage. Instead of having one server for your web server, another for your database, and a third for your file server, all running at low utilization, you can consolidate them onto a single, powerful physical machine. There are two main types of hypervisors, and it is important to know the distinction. A Type 1 hypervisor is installed directly onto the physical server's hardware. A Type 2 hypervisor runs as an application on top of a host OS. Example: VMware SXI. Example: Microsoft Hyper. V. Example: KVM. This is the type used in enterprise data centers and cloud environments. Example: Oracle VirtualBox. Example: VMware Workstation. Running on a Windows laptop. Running on a Mac OS laptop. Great for development and testing, not ideal for production due to host OS overhead. From a security analyst perspective, virtualization introduces both opportunities and risks. Snapshots allow us to capture the exact state of a VM at a specific moment in time. Capture a live snapshot for forensic analysis. Templates or golden images provide pre-configured baseline VMs. Pre-configure it, hardened, patched. However, virtualization also creates new attack surfaces. The hypervisor itself is a high-value target. If compromised, attackers could control all VMs on the host. This is called VM escape. The virtual network between VMs can be invisible to traditional network monitoring. Malicious activity between two VMs on the same host could go undetected. As an analyst, ensure your security tools have visibility into the virtualized layer. Building on the concept of virtualization, we have an even lighter weight and more agile technology: containers. A virtual machine virtualizes the hardware to run a full guest OS. A container virtualizes the operating system itself. Multiple containers run on a single OS kernel, on bare metal servers, or inside a virtual machine. Each container has an isolated view of the file system. Each container has an isolated view of processes. Each container has an isolated view of the network stack. They all share the underlying host operating system. The most popular container platform is Docker. Containers don't need to boot a full OS. Containers start and stop incredibly fast. Containers are extremely portable. This efficiency made containers the go-to for modern app development microservices. Instead of one giant monolith, apps are broken into small independent services. E-commerce example overview. User authentication service, container. Product catalog service, container. Shopping cart service, container. Payment processing service, container. Easier to develop, easier to update, easier to scale. During a sale, launch more shopping cart containers. The ecosystem centers on container images. A container image is a lightweight, standalone, executable with everything needed to run. Managing a few containers is easy. Managing hundreds or thousands across many servers can't be done manually. Enter orchestration platforms. The undisputed leader, Kubernetes or K8s. K8s automates deployment. K8s automates scaling. K8s automates management. Tell K8s to run 5 web server copies. K8s schedules them onto physical or virtual servers. If a server fails, K8s restarts containers on a healthy server. For security analysts, containers in K8s are a dynamic environment to defend. The attack surface constantly changes as containers spin up and down in seconds. Traditional host-centric tools struggle here. Security must shift left integrate earlier in development. Scan container images for vulnerabilities before deployment. Implement runtime security to monitor container behavior. Understand clusters, groups of servers managed by K8s. Understand pod's smallest deployable units that can contain one or more containers. These concepts are fundamental for modern analysts. A critical goal for any IT infrastructure is to be resilient and highly available. HA means designing systems to avoid any single point of failure and ensuring services remain accessible even if a component breaks. This isn't just for disasters, it's for routine issues like a server needing a reboot for patching or a network card failing. Fundamental concept: redundancy, more than one of everything. One web server becomes 2. One internet connection becomes 2 from different providers. Use redundancy with clustering and load balancing. A cluster is 2 or more servers acting as one system. Active-passive. One serves, one stands by to take over. Active-active. All servers handle requests simultaneously. Load balancer sits in front of servers and distributes incoming traffic. If a server fails, the load balancer reroutes traffic to healthy servers. For resilience and disaster recovery, we use 2 key metrics, RTO and RPO. RTO is the maximum time to restore a process after disruption. Example, RTO, 1 hour back online in 60 minutes. RPO relates to acceptable data loss in time. Example, RPO, 15 minutes, lose no more than 15 minutes of data. As a security analyst, know your HA and DR architecture. During incidents, identify critical systems and their RTO, RPO to prioritize response. Ransomware attackers often target backups and redundant components to break resilience. Behind the scenes of every functioning corporate network, there is a set of foundational services working tirelessly to make everything run smoothly. As a cybersecurity analyst, these services are critical to understand and are rich sources of data for threat hunting and incident investigation. The first group includes DNS, DHCP, NTP. DNS translates human-readable names like www.google.com into machine-readable IP addresses. DHCP automatically assigns IP addresses and other network configuration when devices join. NTP ensures devices have synchronized, accurate clocks. Another critical service, the directory service. In most enterprises, this is Active Directory, AD. A directory service is a centralized database of users, computers, other resources on the network. It handles authentication, proving you are who you say you are, and authorization, what you are allowed to do. For attackers, AD is the ultimate prize. Gaining control gives them the keys to the kingdom, allowing them to create rogue accounts, access any data, control any computer on the network. Finally, services that establish trust and manage data, PKI, logging pipelines. PKI is the system of digital certificates, certificate authorities, other components used to secure communications like the browser padlock. Logging pipelines are systems that collect, centralize, and store log data from all systems. Understanding these foundational services is non-negotiable for a security analyst. They are the ground truth of your environment. The final piece of our infrastructure puzzle is establishing a known good state. You can't detect anomalies if you don't know normal. Baselining and hardening are the answer. A baseline is a standardized, documented configuration. Example baseline Windows web server. Example baseline Linux database server. Example baseline corporate workstations, often captured as a golden image. It's a pre-configured hardened template for VMs or containers. Use a CMDB to manage configurations. CMDB stores hardware components. CMDB stores software configuration items and the relationships between them. Hardening reduces attack surface. Apply least privilege. Remove unnecessary software. Disable unused services and network ports. Apply strict permissions on files and directories. Enforce strong password policies and audit logging. For analysts first, they make your job easier. Know the standard and spot deviations fast. Automated comparison tools can flag unauthorized software installations or changes to security settings. Second, CMDB gives critical context. It tells you who the system owner is, what business application it supports, and its criticality. That helps you prioritize response and understand impact. Now that we have a solid grasp of infrastructure components, let's explore how they are all connected. Here's a typical corporate network, not flat, but layered. Think of it like a medieval castle. Outer walls, a moat, an inner courtyard. The keep where the crown jewels are stored. The outermost layer is the edge, boundary between private network and the public internet. Edge devices, primary internet routers, edge devices, firewalls. Just inside the edge is the DMZ, the demilitarized zone. The DMZ sits between the internet and your trusted internal network. Place public-facing servers here: public website, email server, DNS server. If one gets compromised, the attacker is contained in the DMZ. They cannot directly reach your internal network. Behind the DMZ and its firewall lies the core, the trusted network. This is where most assets live. Employees' workstations, internal file servers, application servers, sensitive data. Inside the core, you'll find tighter zones: the data center segment, the inner sanctum, the keep. Houses the most critical systems: Active Directory domain controllers, financial databases, intellectual property repositories. As a security analyst, This layered view is fundamental. It helps you follow traffic flow, judge alert severity by location, and spot potential attacker movement from a less trusted zone like the DMZ into the highly privileged core. One of the most common and fundamental technologies we use for this is the virtual LAN or VLAN. A VLAN, however, allows you to take a single physical switch and logically divide it into multiple, separate broadcast domains. Imagine a single switch with 24 ports. Using VLANs, you could configure ports 1 through 8 to be on VLAN 10 for the sales department, ports 9 through 16 to be on VLAN 20 for the engineering department, and ports 17 through 24 to be on VLAN 30 for the finance department. By default, a computer in the sales VLAN cannot communicate with a computer in the engineering VLAN even though they are plugged into the same physical switch. It really limits the blast radius of an attack. If a workstation in the sales department gets infected with a worm, that worm can only spread to other machines within the sales VLAN. It cannot immediately jump to the critical servers in the engineering VLAN. This practice of dividing the network into smaller isolated zones is called segmentation or microsegmentation. Each VLAN creates a trust boundary. For traffic to pass from one VLAN to another, it must go through a router, or, more commonly, a firewall that is configured to act as the gateway between the VLANs. This is a critical control point. It forces all inter-VLAN communication to pass through a security device where we can inspect it and apply specific rules, which is a topic we will explore in the very next section. If VLANs create the boundaries between our network segments, then firewalls are the gatekeepers that stand guard at those boundaries. A firewall is a network security device that monitors incoming and outgoing network traffic and decides whether to allow or block specific traffic based on a defined set of security rules. The core component of any firewall's logic is its access control list, or ACL. An ACL is an ordered list of rules access control entries, or ACEs. Each rule specifies criteria about a packet source IP address, destination IP address, source port, destination port, and an action to take permit, deny. When a packet arrives at the firewall, it is compared against the ACL, starting with the first rule. As soon as it finds a matching rule, it applies that action and stops processing. If no rule matches, the packet reaches the end and is dropped by an implicit deny all rule. Let's look at a simple example. Permit traffic from any source IP on the internet to the destination IP of our web server in the DMZ, but only on destination port 443 HTTPS. The very next rule might say, deny all other internet traffic to that web server. Modern firewalls go beyond simple IP port filtering. These are next-generation firewalls, NGFWs. NGFWs can perform deep packet inspection, identifying the application inside a packet regardless of port. They can integrate with IPS to block known attack signatures, and they can inspect encrypted SSL TLS traffic. Understanding how to read and interpret firewall rules and logs is a fundamental skill. It's the language of network access control. To protect them, we use a special type of firewall called a Web Application Firewall, or WAF. A WAF operates at the application layer, or Layer 7. It can detect and block attacks like SQL injection, cross-site scripting, or XSS. Another key security component that operates at the application layer is a proxy server, or simply a proxy. A proxy acts as an intermediary for requests from internal clients seeking resources from the external internet. But the real power of a proxy, from a security perspective, is its ability to filter and log traffic A web proxy can be configured to block access to certain categories of websites. Most importantly for an analyst, the proxy server creates a detailed log of every single web request made by every user on the network. We have already touched upon load balancers in the context of high availability, but they also play a significant role in network architecture and security. For example, a load balancer is often the device that performs SSL offloading. The traffic between the user and the load balancer is encrypted, but the traffic between the load balancer and the back-end web servers can be sent in plain text, which simplifies the configuration of the web servers and allows other security devices to inspect the traffic more easily. A well-designed network architecture uses a combination of these technologies in a layered approach, often called defense in depth, to ensure that if one control fails or is bypassed, another one is there to catch the threat. The classic technology for enabling this is the Virtual Private Network, or VPN. A VPN creates a secure, encrypted tunnel over an untrusted network like the Internet. There are two main configurations for an enterprise VPN: full tunnel, split tunnel. A more modern approach to connecting remote sites and users is software-defined wide area networking, or SD-WAN. When you connect to a Wi-Fi network, the first thing you see is its name. This name is the Service Set Identifier, or SSID. However, a newer and much more secure standard, WPA3, is now recommended. This is where 802.1x and NAC come into play. 802.1x is an IEEE standard for Port-Based Network Access Control, or NAC. Modern NAC solutions go even further than just checking a username and password. They can perform health checks on the device trying to connect. One of the simplest methods is to use a span port. For full fidelity monitoring, use a test access point, or TAP. Once we have a copy of traffic, we can analyze flow data, or full packet capture. Flow data is a metadata summary of network conversations. Full packet capture, PCAP, is the opposite. It records everything. In practice, organizations use a hybrid approach. Collect flow data network-wide for broad visibility. Use PCAP on a rolling basis at choke points. So far, we have focused entirely on the world of information technology, or IT. Now, we pivot to operational technology, OT. OT is hardware and software that detects or causes a change by monitoring and controlling physical devices and processes. Systems that run a power plant, systems that manage a water treatment facility, robots on a car assembly line. The core difference is priorities. In the IT world, we often talk about the CIA triad: confidentiality, integrity, availability. In OT, the pyramid is inverted. OT's top priority: availability and safety. An IT admin might reboot a server after applying a patch. Rebooting an OT controller could stop an entire production line. OT often runs 20-year-old operating systems like Windows XP or older proprietary systems. As a cybersecurity analyst, you must understand and respect this fundamental difference. You cannot simply apply IT security playbooks to an OT environment without understanding the potential impact on the physical process. The most common type is the Programmable Logic Controller, or PLC. A similar device you will often encounter is the Remote Terminal Unit, or RTU. This is the job of the Human-Machine Interface, or HMI. Two terms: DCS, SCADA, Distributed Control System DCS, found within a single confined industrial site. SCADA supervisory control and data acquisition designed for processes spread over large areas. Many traditional OT protocols lack even the most basic security features like authentication, encryption. One of the most ubiquitous protocols you will encounter is Modbus. In the North American electric utility sector, a more advanced protocol called DNP3. Another important protocol, especially in building management, is BACnet. The universally accepted framework for achieving this is the Purdue Enterprise Reference Architecture, often just called the Purdue Model. The most critical boundary in the entire model exists between Level 3 and the levels above it. This IDMZ acts as a buffer between the OT and IT networks. The fundamental rule of the Purdue Model is that traffic should not jump levels. Specifically, there should be absolutely no direct communication path from the IT network at level 4 or 5 into the core OT control network at level 2 or below. We must rely on compensating controls. The most important compensating control is robust network segmentation. Other critical compensating controls include network monitoring and intrusion detection. Every piece of software you run executes as a process on your computer. It is a living, breathing instance of a program that the operating system is actively managing. The operating system, or OS, gives each process its own private space in memory. It allocates a specific isolated block of memory to each process and ensures that one process cannot accidentally or maliciously access the memory belonging to another process. This formal request is called a system call. A system call is the bridge between a user-level process and the powerful, privileged core of the operating system known as the kernel. Advanced monitoring tools, known as endpoint detection and response, or EDR agents, work by hooking into these system calls. They watch every request a process makes to the OS, allowing them to spot the suspicious patterns of behavior that are the hallmarks of malicious activity. Underneath every operating system is something called a file system. The file system is the structure that the operating system uses to control how data is stored and retrieved. Common file systems you'll run into include NTFS New Technology File System on Windows, ext4 on Linux, XFS on Linux. Beyond organizing files, the file system enforces one of the most critical security concepts, permissions. File permissions determine who can do what to which files and directories. The traditional Linux permission model is simple and elegant. Every file and directory has 3 sets of permissions attached to it. One for the user who owns the file, one for the group the file belongs to, and one for others, everyone else. Windows, from the ground up, was designed around a more granular permission model using ACLs. Misconfigured ACLs on Windows file shares are a classic source of internal data breaches, making ACL auditing a critical task for security teams. In the Windows world, the primary source of this history is the Windows Event Log service. For many years, the standard on Linux and other Unix-like systems was syslog. In recent years, many modern Linux distributions have adopted a newer logging system called Journaled. To truly supercharge your endpoint visibility on Windows, Microsoft provides a powerful free tool called System Monitor, or Sysmon. For a threat hunter, Sysmon data is pure gold. Patching is applying updates to software to fix these vulnerabilities. Maintain a consistent, timely patch schedule. It's a vital security control. Debian, Ubuntu use APT Advanced Package Tool. Red Hat, CentOS, Fedora use Yum. Modern successor, DNF. SUSE and derivatives use Zipper. To be a truly effective and efficient cybersecurity analyst, you need to learn how to speak the language of automation. But having a basic proficiency in scripting and coding is a massive force multiplier. Python, PowerShell, Bash. With a simple Python script, you can read the list from a file, loop through each IP address, make an API call to VirusTotal for each one, and save the results to a report all in a matter of minutes. A command line tool like grep combined with regular expressions or regex can find what you need instantly. This directly ties into the work of every analyst and even aligns with certifications like CompTIA's CISA Plus. It is the key to unlocking the next level of your analytical capabilities. All right, we have covered a tremendous amount of foundational theory. Now, let's make this real. Today, we are going to look at one of the most widespread and impactful security events of recent times, the mass exploitation of a vulnerability in a piece of software called MOVEIT Transfer. MOVEIT Transfer is a managed file transfer, or MFT, application. Companies use it to securely send and receive large files, financial records, healthcare information, personal employee data. In May 2023, a notorious Russian-speaking ransomware and extortion group known as Klazera discovered a critical vulnerability in the MOVEIT Transfer web application. This was a zero-day vulnerability, meaning it was unknown to the software vendor and the public, so no patch was available when the attackers first began their campaign. The attackers did not deploy ransomware in the traditional sense of encrypting the victim's systems. Instead, their goal was pure data theft. They systematically and automatically exploited the vulnerability in every publicly accessible MOVEIT transfer server they could find on the internet. After they had stolen the data, they then began the extortion phase, contacting the victim organizations and threatening to publish the stolen data online unless a ransom was paid. The impact was enormous, affecting an estimated 60 million individuals. So, how did the attackers get in? The vulnerability they exploited was a specific type of web application flaw known as a SQL injection. A SQL injection vulnerability occurs when the application fails to properly sanitize or validate the input it receives from a user before including it in a SQL query. This allows an attacker to inject their own malicious SQL commands into the query. They use their malicious SQL queries to upload a special file, a type of malicious program called a web shell, onto the MOVEIT server's file system. Once this web shell, which they named Human, ASPX, was placed on the server, the attackers had a persistent foothold. This is a classic attack chain. It starts with a single vulnerability in one layer of the technology, stack the web application, and then pivots to gain control over another layer, the operating system. If you were a security analyst at one of the victim organizations, where would you even begin to look for signs of this attack? The very first place to turn would be the logs generated by the web server. An analyst could therefore search their IIS logs for any requests to a file named Human ASPX. Since this is not a legitimate file in the MOVEIT application, any log entry showing a successful request to that URL would be a high confidence indicator of compromise. An astute analyst could look for anomalies in the SE bytes, that is, server-to-client bytes field of the IIS logs. A sudden spike in outbound data transfer from the MOVEIT server, especially to an unfamiliar IP address and happening at an unusual time like the middle of the night, would be a major red flag that something was wrong. This brings us to our first hands-on thought exercise. Pause for a moment and put yourself in the analyst's shoes. You have just been told to investigate a potential MOVEIT compromise. you have access to the raw IIS logs from the server. What specific command line tool on Linux or PowerShell command on Windows could you use to quickly search through gigabytes of these text-based logs for any mention of human ASPX? So, you have found the initial evidence in the web server logs. Your investigation needs to pivot from the web application layer to the underlying operating system. Your first step on the server itself would be to look for the human.aspx file on the file system. You'd also examine the file's metadata, like its creation timestamp. This is where a tool like Sysmon, which we discussed earlier, becomes really indispensable. If Sysmon was installed, you could filter for all child processes created by the IIS worker process, W3 WP.exe, around the time the web shell was being accessed. Pause and think about this scenario for a moment. You are looking at the Windows security event log on the compromised MOVEIT server. What specific event IDs would you search for to see if the attacker tried to create a new user account or log in with different credentials? What if they tried to access files outside of the MOVEIT data folder? What event IDs related to object access auditing would be relevant? The workflow is a process of discovery, pivoting, correlation, connecting evidence across technology layers. Think of the knowledge from this chapter as a powerful flashlight. When you're thrown into the dark and confusing environment of a security incident, most people see shadows and chaos. But with your flashlight, you know where to point it. We have covered a massive amount of ground in this chapter. We started with infrastructures and architectures. Next, we explored network architectures. We took a special detour into operational technology. Then we dove into the heart of every device, the software. We then equipped ourselves with coding for analysts. It is incredibly important to understand that this chapter is not just a collection of unrelated technical facts. Every single concept we have discussed forms the essential substrate, the underlying layer for all the advanced analyst workflows we will cover later in this course. To help you solidify the concepts from this chapter, let's finish with a few self-assessment questions. Here is your first question. What is the fundamental difference in security priorities between a traditional IT environment and an operational technology environment? And why does this difference matter when responding to a security incident? Next question. You are investigating a Windows server and suspect a malicious process is running. You have access to the standard Windows event logs and Sysmon logs. Describe two specific event IDs or log sources you would examine to identify the suspicious process and understand its activity. Finally, our last question. Explain the purpose of a DMZ in a network architecture. What kinds of servers would you typically place in a DMZ? Web servers, mail servers, DNS servers, and what is the primary rule of traffic flow between the DMZ, the Internet, and the internal trusted network? Mastering these basics is what gives you confidence when you are in the Security Operations Center. It allows you to act decisively and intelligently when faced with a potential threat. In the next chapter, we will dive into the analyst tools and workflows that build directly on these very foundations. Thank you for your attention, and I look forward to seeing you then.